Hello, welcome. We are talking asynchronously about a sampling distribution of a sample mean. This topic is real complicated and real important to statisticians. For those of us who are not statisticians, that's most likely you and definitely me. I teach people about statistics. I'm not a statistician. But this is a really important topic, fundamental in the discipline of statistics. We'll try to make clear what that means as we go. Okay, the central limit theorem of statistics is what we're talking about in this section. CLT for short. You can see those little arrows are meant to indicate the central limit theorem is the connective tissue between descriptive statistics, like we studied back in chapters 1 and 2 of our textbook, learning about data and how to describe it with graphs and statistical descriptions, summary statistics or graphical displays as you see on the slide. That's understanding sample data. Go get a sample from a large population, measure some stuff, count some stuff, describe some stuff, and then try to understand what you've learned about that stuff, descriptive statistics. The central limit theorem allows statisticians to use, analysis, probability, and mathematics to then make an inference about the larger population based on statistics they study from their sample. That allows statisticians to estimate a parameter, a characteristic of a population they're curious about using a confidence interval, which gives your statistic a margin of error based on how you expect things to vary from sample to sample, or to do a hypothesis test, which lets statisticians check how likely their sample data looks under an assumption about the larger population. Yeah, big deal. So statisticians really care. The way that our textbook and most stats textbooks present the idea is by starting by looking at a population. So we're going to look at a population, the number of basketball games attended by some people in North Carolina, where the person who made our slides works at Duke University. Dang it. My throat has got a little tickle. Here is population data for the number of basketball games attended by some people in North Carolina who were surveyed by a stats teacher sometime. We've got a couple of questions as we look at this distribution. Let me pause this because I can pause things while I'm making a video. The pausing is over. Let's look at this population distribution. So we got a couple of questions we'll consider. Let's look at the picture to consider these questions. That distribution there, they're asking if that is symmetric or skewed. If so, which way? Well, let's give a little opinion there. Let's say, hey, what do you say, class? There's nobody here, it's just me. Symmetric or skewed? Hey, Ralph, it looks skewed. Yeah, I heard someone say it looks skewed. Yeah, it looks kind of skewed to the right. Yeah. So yeah, this is skewed right. A lot, right? We see a huge peak in the low values between 0 and 10. Over 150 people who've seen up to 10 basketball games in this data set of a population. Most of the people in this population of about 200 people. Maybe 20 or 25 of them have seen between 10 and 20 games, and very few have seen more games than that, skewed off to the right. Estimating the mean visually, remember back in chapter 2, we talked about doing that, and what we said was to estimate the mean is at the balance point. If we imagine all of that blue histogram space is if it's all got weight. So let me draw a little balancer here. Like a little triangle is my style, like the fulcrum of a teeter-totter. Put that down there on that axis. And if I use my eyeballs, it could not be right in the center of that at 5. That would just be, it would tip over due to that skew to the right. But if I just drag it a little closer, you know, you don't have to go much higher than 5 because that first bar is so big. I would estimate the mean being, I don't know, about around 6. So visually near 6 games mean on average. Right? 6 games on average would be my guess for the population mean here. Okay, now we're going to come back and think about skewness and looking at means visually as we talk about sampling distributions. Okay, let's go talk about them. Okay, average number of games attended. Let's look at the sampling distribution of the sample mean for samples of size n equals 10. Okay, and there's a graph. You can see that the label here, what they're talking about is sample means from samples of size n equals 10. What they did was, considering the population on the previous slide of about 200 people and how many basketball games they'd seen over some course of time, maybe a year, they said, dear computer, randomly select 10 people's number of basketball games from that population, take the mean. And do that a few thousand times, I think about 5,000 times, and then make me a histogram. So we're looking at a graph of about 5,000 random samples of 10 people from the population's number of games seen averaged. So like each 10 people average the number of games they saw, plot. That's the picture, a sampling distribution of the sample mean for samples of size n equals 10. Okay, what does each observation in the sampling distribution represent? That was kind of at the beginning of my little story. Tell the computer from the population on the previous slide, that very skewed to the right population, draw 10 numbers at random of the number of games people saw and take the mean, one single sample's mean. Hey, check, I got it. One sample mean, X bar being the symbol in statistics, from one sample of size n equals 10, randomly drawn from the population on the previous slide. Okay. Is the variability of the sampling distribution smaller or larger than the variability of the population distribution? Okay, the population distribution's on the previous slide, so we can't see them both to compare. Let's go back and look at it. The simplest measure of spread on a graph like this would just be the range, the approximate range. So I'm just going to look all the way across from the first, pardon my video making skills failing me there, from 0 up to about 70, the population's range is something like 70. Let's put that in a little green note right here in my notes. Population range about 70. Let's make that green like the arrow I drew. Okay, let's go back and look at the samples of size 10's means range on the next slide. Okay, look at that arrow that I drew down here. It's way too big for this thing. So if I shrink it down, looks like sample means samples of size n equals 10, the range is about, I don't know, between 0 and 20 or so, about 20. Sample means I'll put n equals 10 in parentheses, range is about 20. Wait, let's double check the question one more time. hard to read my work down here. Scoot that down. Is the variability of the sampling distribution smaller or larger than the variability of the population distribution? Anyone in class have an idea? I've got an idea, Mr. Yutz. Oh, yeah? What do you think? Well, population range is much bigger at 70. So that means the sampling distribution has a smaller range, less variation than the entire population. Hey, really good. Great observation, fictional student with kind of a Muppety voice. Now, why is that? Oh, good question, Mr. Yutz. Well, when you add up 10 numbers, take a sample of 10 and add up the 10 numbers and divide by 10, the big number any big numbers get added to the little ones, and the average is like toward the middle. So it brings the numbers toward the middle. Does that make sense, Mr. Yutz? Yeah, let's see what the slide has to say. Smaller, agreeing with our Muppet-voiced fake student character that I don't know why I'm doing. Sample means vary less than individual observations. Yeah, and it's because the individual observations could be spread out from as low as like 0 games up to that somewhere in the 60s for that one person in the population who's had tons of games. But even if you pick that tons and tons of games, it's going to be added up to 9 game numbers that are lower. Take the average, it's going to bring them down closer to the center. Okay, interesting. All right, what's next? Oh, this slide is from a previous time. I talked this through with a different class. I think I dumped it in there because someone in the class said, "Hey, Ralph, can you dump that slide into the slideshow?" And I said, yeah. So we have a blank one like this right here. Average number of games attended. Now, let's compare the sampling distribution of the mean for samples of size 10, which we saw on the previous slide and is here on this slide in the lower left, versus for samples of size 30, which we see here on the lower right. And let's take they have 3 questions here. How did the center, spread, and shape of the sampling distribution change as we go from sample size n equals 10 to sample size n equals 30? So we'll think of it like this. Sample size, I think of in terms of blue. So from 10 up to 30, we're kind of going, this way, bigger samples, okay? And let's take these one at a time, starting with the center. How did the center change as we shifted the sample size? Let's draw my little fulcrum that I like for estimating the mean. Visually, I'll draw 2, one for each sampling distribution. Get my fulcrum mover here. That one, you buy that? Is that a little bit too much to the right? Maybe slightly less than 6. Slightly less than 6 might balance out for the mean of the sampling distribution for sample means from samples of size 10. Okay, and then if I do another balancing here for sample means of samples from size 30, hey, looky there, somewhere between 5 and 6. Looks like a pretty good, maybe a little closer to 6 than 5. Okay, so the centers look the same. Let's put that in my notes. Centers look about the same. I'll put that in orange for my center color that I like today. Okay. Okay, next question was the spread. We used green arrows on the previous spread examination. Let's go get some arrows, make them bright green. Samples of size 10, well, now with more detail here on the axis, that spread might go from around 0 up to about, looks like 17 or 18. I don't know. And then the spread for samples of size 30, if I draw another green arrow, it goes from a little more like maybe 2.5 up to about, I don't know, 10.5. So that's about 8. Spread, green is my spread. larger spread for the smaller samples means. Okay? Smaller spread for the larger samples means. Let's write that down. Kind of hard to say. Larger spread for smaller samples means. Okay. And over on the other side, over here, smaller spread, less variation for larger samples means. Yeah? Okay. And the third question is the shape. They're thinking about symmetry or skewness. Let's grab another. I think pink will work pretty well. Oh, wait a minute. I just turned something green pink by accident. Okay. I'm going to grab a pink highlighter. You can see here we can draw in this lovely skewed to the right curve for sample means from samples of size 10 from the population. And if we draw in a curve here, it's also skewed to the right, but to my eyes, not as much. I hope you'll buy that. Less skew for the larger samples means. That's what I'm seeing. So less skew for larger samples means. And likewise, in the other one, I see more skew for smaller samples means. Okay, so there's some trends we're seeing. Let's see how the slide answers the question. Center is about the same, which agrees with our notes. Spread is smaller for the bigger samples because we're going from 10 up to 30, okay? And shape is more symmetric or less skewed as we put in our notes. More symmetric for larger samples, less skewed. Okay, there's a pattern that's happening now. We can kind of see that's the goal of our, or we're looking for these patterns. What's happening to the center, the spread, and the shape of these sampling distributions as we get larger and larger samples. Consider how their means vary from sample to sample for larger sample sizes. It's hard to say all that, these sentences. It's taken me years of practice to even be able to say them out loud. If they don't seem to make sense to your ears, hearing about this for the first time, that's normal because this is actually really complicated and takes most smart people lots of time and thought to really understand well what we're talking about. Thousands of samples from a population, considering means of one thing from those samples and comparing them in a big distribution. That's a complicated concept. And then to think about what patterns we see as the samples get bigger is a bonus level of complication. So if you're just doing your best to make sense of this in both listening to this discussion and your reading, and you ask your questions when they come up, especially on your homework assignment, you're doing the best you can to understand this in the brief time we have. I think I'm going to take a screenshot of this exact screen right here, just in case we want it for later, just to have it. All right, I'm just going to take a screenshot of this. Oh wait, nope, not that screenshot. I can't see everything. I'll take a screenshot of the good stuff in the slide, and then if we need it, like maybe for the slideshow or for our notes later, we'll have it. All right, got it. Okay, so at least that's somewhere in my computer. We're not going to lose it when we hit clear. Oh. Okay, next slide. All right, here we're looking, you'll notice the sample size got bigger. We're now looking at samples of size n equals 70. So, dear computer, from that population of about 200 people who saw some basketball games, grab 70 at a time at random. Take the mean number of basketball games among those 70. Do that a few thousand times. Show me a histogram. Here's the sampling distribution for samples of size 70. We can see now that the shape of this thing is wildly symmetric. If I try to draw a smooth curve through the peaks of those bars, that looks like a normal curve, a bell curve. Estimating the mean value here, we can see it's like, I could just put it right near the middle of that big old central bar. It's about 5 3/4. Very similar to the estimates we had in all of our previous pictures we looked at. Somewhere near 6 in the population where we could see less detail. And then between 5 and 6 and closer to 6 was our estimate for samples of size 10's mean of the sample means. And for samples of size 30's mean of all the sample means. Whew. Okay, and then the other thing was the spread. We looked at that in green with an arrow, and here the spread is down to, I don't know, just about 7 3/4 down to 3 3/4, about 4. So the smallest spread we've seen in all these groups. Bigger sample size, we get, well, easier to see where the mean in the population is because the variation is getting smaller and smaller, and it's getting more and more symmetric. Less variation, more symmetry, closer and more consistent relationship to the population parameter. In this case, the population mean. I would guess it's 5 3/4 now. Kind of cool. Heck, while we're here, let's grab a little screenshot just in case we want it. You can't have too many screenshots. Just grab them. Have a screenshot, buddy. Oh, and then this practice question looks like a few of your homework questions, if I remember. At the top, you can see a population distribution. So let's call it red. The mean is 7, sorry, the mean mu in that population is 10. So if I want to draw in my little balancer for the mean, it's going to go at 10, exactly. That's cool. And right now, we should be able to guess that in all of the distributions below, because they're all sampling distributions, the balance point should be near 10. And then the standard deviation there is about 7 for that distribution, or its complete range is about, well, almost 50. So get a sense of those numbers. Let's just draw in my pictures here. Green is what I like for the range. I just go 0 up to the top, about 50, okay? Yeah, close enough. And then they ask us, determine which plot A, B, or C goes with each of the following. A single random sample of 100 observations from this population. Think of those as samples of size 1, right? So n equals 1 would be what we'd say about the sample size here. N equals 1. For the second option, size 7 is n equals 7. And for the third option, the sample size is 49. So we've got number 1 here is the smallest samples, size 1. Number 2 here is the medium-sized samples, size 7. And the third option is the biggest samples, size 49. And for the larger groups, take the means of the samples and plot them, just like we talked about before. Sampling distributions showing how means vary from sample to sample. Okay, Let's do our artwork that we've done on previous slides. We've considered how this affects symmetry. So I'll just, through the peaks that I can sort of see and trace, plot A down there on the lower left looks pretty skewed to the right. Plot B looks still more skewed to the right. The tail like comes is more taily looking, and plot C is the most symmetric. So let's take a couple notes there. Plot C is most symmetric, and plot B is least symmetric, right? Okay, we can also double check that the thing that changes as we made the sample size bigger and bigger was either more symmetry for bigger samples. So plot C should, it's the most symmetric by far. That should probably be number 3, samples of size n equals 49. But just to double check that we're on the right path, let's double check the ranges, right? The range should shrink for larger and larger samples. I'll go back and make some green arrows like on our previous slides. For plot A, it's about 14. For plot B, about 35. And for plot C, it's about, I don't know, a little more, about 4. So just quickly noting those sizes. Range 18, 14. This one here. Range about 35. And then the last one, range about, I said 4, yeah, maybe slightly more than 4, but I'm not going for perfect accuracy. But so the biggest range should be for the smallest samples. So plot B should align with, biggest range. Let me go this way. Biggest range and least symmetric, that should be the smallest group, n equals 1. So I'm saying plot B, n equals 1. Let me use a different stamp. We can also see the smallest range is range 4, and the most symmetric graph is plot C. So plot C should be the third one, okay? So I'm thinking it's going to say B for number 1, A, which is just in the middle, for number 2, and C for number 3. I'm going to write my guesses out here in blue. How did I do? B, A, C. Am I right? Let's check my work. Did that sound like an excited stadium full of Zoom session viewers? Though we're just checking this out via a recording of a Zoom session. I got it. The distribution looks the most like the population. You can see there. So for samples of size 1, and we can see the least spread and the most symmetric is samples of size 49. The one kind of in the middle, just less spread than the others, than the smallest samples from description 1 above, and not as much spread as the population, but more than for the largest samples is plot A. So that falls in there at number 2. Pretty cool. You'll see a couple more of these, I think, in homework, or maybe sometimes I put this on an exam. So I might have cut and pasted one of these for the exam. I can't remember. Good problem though, because it illustrates the technique here pretty well. Let's grab a screenshot of it while we're here. Okay. Now let's go to the next slide and see what it says. The central limit theorem. We've been looking at kind of examples that show or it's really one example, the big one about the basketball game watchers, about 200 people in the population. If we were to take larger and larger samples from that population, we'd see distributions of samples means that get more and more symmetric and more consistent. And the consistency is closer and closer to the population mean. This says that sample statistics, in particular, a sample's means, are kind of predictable. If you know something about the sample size, you can learn something about how much variation you expect and how symmetric you expect things to be. Statisticians love this, and that's why the central limit theorem is one of the most important results in the history of the discipline. And here's an informal rendition of the central limit theorem for sample means. As the sample size n gets larger, the distribution of sample means becomes more normal, so more unimodal, and especially more symmetric, regardless of the shape of the population distribution, whether or not it's skewed, and more consistent, that is, a smaller range and standard deviation among the sample's means for samples with larger and larger size. Couple of caveats. The central limit theorem requires random samples from a large population with fixed mean and standard deviation. That's cool. Actually, and the sample size required kind of depends on the population shape. If the population is unimodal and symmetric, you can get away with tiny samples like size 2. If the population is very skewed or multimodal, you need larger samples for this theorem to work out. And we get into those details in other sections later. I think we actually don't get to them until like Stats 2, Math 244. Plug. Want to take Stats 2, Math 244 in an asynchronous online format this coming fall? Sign up when you can. I'll teach it for the first time online. It'll be weird and different and new for me. And you, if you take it. Yay! The applet that demonstrates how this works at the bottom of the slide is good when we're kind of in person and I can vibe how people's faces are squinting at what I'm talking about. I have never used that applet as an example in remote classes. So if you want to explore it and see if it makes some sense to you just for fun, open up the slides through D2L, Brightspace, copyright, trademark, large corporation, and explore. If it makes sense and helps your understanding, cool. If it confuses you, write down a question about that confusion and bring it to class the next time we meet together and we can talk about it. Or, contact me outside of class if you aren't able to make it to our class sessions. Okay, now I'm going to pause this video recording for just a minute to catch my breath. We're going to get into some details of how this works and see an example of how the central limit theorem can be used to do a calculation of a probability that actually kind of makes sense to calculate. So let me pause and I'll come back in just a minute. Okay, that pause is done. Now let's look at this summary of what the central limit tells us about the sampling distribution of samples means. They didn't draw the picture for us, so I'll draw it on the slide. And as we read through this, we'll illustrate the picture with the symbols and the concepts a little bit more. Okay, I'm drawing the best. I'm drawing a semi-unimodal and semi-symmetric curve. 3 important facts about the distribution of samples means for samples of the same size drawn from a large population. So that's why it's blue. That horizontal axis I illustrated is values of different samples, sample means, samples of the same size. So sample size n, set sample size n. Okay. The mean of samples means, we kept illustrating that in orange. The mean of samples means has this notation mu subscript x bar. And it's equal to, I'm going to color it in red, just mu, no subscript. That's the population mean. Okay, so let's put that in our little notes here. Equal to mu. Mu is population mean. Okay. So the center of this curve, when I draw it in, I will draw it in with a bright red line, because that mu subscript x bar is actually the population mean mu. Okay. Well, let me try to write that in there with a little artistic. Let me grab my drawing device. That mu, just that population mean mu, that is the mean of the sample means, the little balance point that we kept drawing with our orange balance. Right there. That's pretty stylish. Little red mu inside a cute little orange. Hey, buddy, come here. Buddy, pal. There you go. All right. Okay, and the standard deviation of all these samples means, which in our graph is going to be about this big, right? To capture about, maybe we should go with green for that color, actually, sorry. Variation, right? So maybe we should go with green. If we capture about 2/3 of the area under our curve, that should take us 1 standard deviation in both directions. So that means our standard deviation of samples means. The notation is sigma with a underscored x bar. Sigma for standard deviation, x bar representing all the different samples of the same sizes. Mean. Means sigma x of x bar. Standard deviation of sample means. It's equal to, you can see that formula right there, the standard deviation sigma, which I'll use red again. That's the population standard deviation sigma divided by that n is the sample size, right? So there's this crucially cool relationship right there. The population standard deviation, that's something about the population, having a direct relationship in this sampling distribution of the sample means to the sample size. That's the crucial connection of the central limit theorem between descriptive statistics, sample size, and inferential statistics, talking about the population. Statisticians love that. So for my notes, I'll write that in those colors. The number sigma is part of this calculation right here, but I'm going to divide it by the square root of the sample size n. So there's my sample size, and there's that square root symbol. Whew, looking good. Okay, and when you get that set up, you can then talk about the probability of finding samples with certain means. And what's that for? Well, we'll look at that in a nice example. You'll notice the caveats are down there in the third point. If the population is normal or if the sample size is 30 or more, this tends to work out as long as they're random samples from that large population. So either a normal population or fairly large samples, at least size 30, and this works great. Pretty cool. Okay, I'll do it again. I'll take one more screenshot as we go. I'll just screenshot all these things. Okay. I'm starting to get my idea where the screenshots are actually going to live for us this quarter. I've got an idea. But let's move on. I think we have one example of how this works in practice, and that's kind of it for us. Yeah, and the example comes from the world of manufacturing. A manufacturing process is designed to produce bolts with a 1/2 inch diameter. Once each day, a random sample of 36 bolts, so that's our sample size, is selected, and their diameters get recorded. If the resulting sample mean is either below 49/100ths of an inch or greater than 51/100ths of an inch, they shut down the manufacturing process to adjust machinery. The standard deviation for diameters is 0.02 of an inch, and that's a population standard deviation, read in all my notes before. And heck, they're going for a 0.5 inch diameter. That should be the population mean. Question is, what is the probability that the manufacturing line will shut down unnecessarily? So how likely is it that they end up with a sample who's like got a mean of less than 49/100ths of an inch or greater than 51/100ths of an inch? Their hint is find the probability I just described when the process's mean is, as stated above, a 0.5 inch mean. Okay, whew. Ready to work through this one at kind of human speed? I think we'll work through it in our class notes Jamboard. That's a place that we can work on this at human speed, and it will save my notes for you to look at if you like. I'll pause the video while I go open up the Jamboard. Okay, now I'm here at our class notes Jamboard. This is linked in our course information module on D2L Brightspace Trademark Copyright Large Corporation. Labeled here on the 9th frame as sampling, distribution, manufacturing example. Information back on the slide that we need to get over here. Let's go look for it together. The process's mean is 0.5 inch, so that's our population mean. So the symbol is mu, and that's 1/2 inch population mean. The standard deviation in the population, they told us that, and its symbol is sigma. I believe it was 0.02 of an inch population standard deviation. Let me double check that. Yep, I got that right. And then our goal is to find the probability that either sample means for samples of size 36, sample size, let me get that in my notes, n equals 36 sample size. The goal is to find the probability that either sample mean x bar is less than 49/100ths of an inch or sample mean x bar is greater than 51/100ths of an inch. That's in symbols. The question they asked there, what is the probability that the manufacturing line will be shut down unnecessarily? So assuming the population mean is 1/2 inch, how likely is it that we'd see this all get shut down? Now let's go back here and make a little note. Notice the questions about the probability of a certain sample mean coming back. Question about probability of a sample mean being in a specific range. Being in a specific range, we use the central limit theorem. Ding, ding, ding. That's like the important little, like, your eyeballs when you see that fact, the question being asked about a sample mean in a certain range. We're going to use this central limit theorem. Now what that means is sample means should vary normally, right? We have more than 30 in the sample, 36. That's a big enough sample for this to work. So we can draw that blue curve that I drew on the slides before. It doesn't look as beautiful as before because I don't have my straight line drawing tool here in the Jamboard. It's going to be centered at, remember, the center of this thing is at the population mean. So it's going to be right there at 1/2 inch. I can label it with a number right here, 1/2. And also we can calculate the standard deviation using the central limit theorem. So this amount right here, the calculation for standard deviation and I should write this down right nearby. The standard deviation, oops, not like that. I should type it here using the tools of, wait, yeah, okay. The standard deviation of sampling distribution. Oh, wait, my notes should also include the mean, because this is new to y'all. I'm going too fast. The mean of sampling distribution is population mean. That's 1/2, right? Bam. Standard deviation of sampling distribution is a calculation. Population standard deviation divided by square root of sample size, okay? And they have symbols, but it's like sigma subscript x bar. It's not easy to type. I'll write them in there. So this is population mean is the mean, sorry, the mu is the mean, subscript x, wait, that's not how you write mu man. Right, yeah, mu has like this, mu subscript x bar, that's the mean of the sample means, that's the population mean, 1/2, and sigma subscript x bar, that's the standard deviation of the sampling distribution, population standard deviation, sigma, divided by, so this population standard deviation for us is up here, that's 0.02, and the sample size, oops, what am I doing here? Buddy, what are you doing? Sorry, I'm using Zoom and Jamboard. I sometimes get confused with which pen I'm grabbing. Population standard deviation here is 200ths, that's that number. Sample size, n, is 36, right? There's our n. That's this 36 right here, the sample size. So that's going to be a little calculation for us to write there into our notes. Standard deviation is going to be 0.02 200ths divided by the square root of 36. I'm a nerd. I know what that number is. That's 0.02 200ths divided by 6. And I love fractions. That's going to be, if I reduce the fraction, 0.1, so 1% divided by 3, that's going to be 1/3 of 1%. So 0, 0, then a bunch of 3s. And in my notes, I can label it in my drawing, just, you know, here, 0.00. Oh, it's hard to fit in there. And then as many 3s as I would ever want to type. That's my standard deviation in the picture. Okay, now the cool thing is in my picture, I can tick off 1, 2, 3 standard deviations in both directions. 1, 2, 3. And because I'm a math nerd, well, that's 1/3 of 1%. So I know that my 4900ths is down here. This 4900ths that we had back in our problem, the chance that we're below 4900ths or above 5100ths, that's 3 standard deviations above. Okay, check that out. That's cool. Now we can even draw a picture of this probability if I just draw a little border at those values and I think of the area out beyond them, like that area out there and this area up here. Once I've got that calculated, I know my result. So I'll do that over in GeoGebra. Once we've got the correct, you know, the sampling distributions, mean and standard deviation, see the right side, see work on the right. To the right, we calculate the probability using our buddy GeoGebra. Let's go over there and do that. www.geogebra.org/classic#probability will take me directly to GeoGebra's normal probability calculator. Heck, back in my notes, let's just put in the entire website number. We're going to type in 5/10 for the mean, mu, in GeoGebra. So there's 0.5, 5/10 centers the curve at 5/10. We're going to plug in 1/3 of 1% for the standard deviation. I just 0.00 and then as many threes as I ever want to type. And I've got the standard deviation correct. And then we're going to look, let me grab my pointer. Love my little pointer. We're going to set it to that little symbol there. Lets us look in for the area out in the two tails, beyond the numbers out into the tails, like in my drawing with that green area. So I'll select that one. You can see the tails light up. Then I'm just going to enter my values, 0.49 from my drawing and from the original slide, and 0.51 being more than 100th off for the sample mean. It's a mean for a sample of size 36. The chance of that happening, if the machines are all working properly, you can see right there, it's less than 0.3 of 1%, or it rounds off to 0.3 of 1%. Let me get this screenshot for folks who want to see how to do this later. That's enough of that to see everything there. Maybe like that. Pardon me. There's our result, 0027. Head back to my work. Probability that we have a value below 49% or a value above 51. Sorry, I'm saying percent. Those are inches, 49/100ths of an inch. The sample mean for the bolt size being below 49/100ths of an inch or above 51/100ths of an inch is 0027. There's only about a 0.3% chance of shutting down the process unnecessarily. And if you're a bolt manufacturer, that's pretty cool, right? You have a very low chance of turning off the machine if you're making these bolts. I'm going to try to draw a bolt pretty fast just to get this to be more art. That sank. Come on, little bolt. An octagonal bolt like that. So it's got like an octagon. Most bolts are hex bolts, right? Very few are octagonal. But it's fun to draw a bolt after talking about bolts for that long. It's fun to just take a little time to do a little bolt drawing. The threads inside there, little artistic time spent making a bolt. But that's good. They don't have a high chance of shutting down this process unnecessarily. So the factory can confidently be making bolts and doing their best work. That's that example. That's how that works. Now, again, the key step here, let me emphasize it. When you recognize this question about probability of a sample mean in a certain range, it's a central limit theorem problem. The crucial thing there, oops, there's an extra letter right there. Sorry, bad spelling. we have to get the standard deviation calculated correctly. So it's this standard deviation adjustment that I made right here that is really the crucial step to getting that number right. Population mean was no problem, we just grabbed it. But once we have both the population mean plugged into the sampling distribution and the correct standard deviation of the sample means, using that starred formula down below the drawing, then it's not a problem at all to calculate a probability using our buddy GeoGebra. Yay! Wow, that's the whole slideshow. I think there might be a couple of other slides on there that have alternate illustrations of this example from olden days in different class meetings. You can check them out for a different look at this just in my notes. But this is the one example we have for this discussion today. As you work on your homework, yeah, ask your questions. We'll be back to class together, not this, but the following week. And if you've got questions about sampling distributions and the homework problems in the second section of chapter 4, you will be a great class hero to me and to your classmates. Oh, hey, while we're doing these video classes, let's just save our participation quizzes until we're all together again. That way we can at least talk about them and they can serve as like a little bit of mini review for the topics you've talked about, I've talked about, we've talked about, I've talked about. This is weird. The topics of the week. All right, have a good one. Bye, video.